Picture the moment someone first tasted cooked food, not as a deliberate experiment, not as a culinary innovation, as an accident, the most consequential accident in the history of the human species, and possibly in the history of life on Earth. A wildfire has passed through the landscape, maybe lightning struck dry grass, maybe a volcanic event, maybe the kind of slow burn that moves through savanna woodlands in the dry season and reshapes the ecology in ways that the animals living there have been navigating for millions of years. The fire is gone now. What remains is blackened earth, ash, and the remains of animals and plants that did not escape, some charred, some partially cooked by the heat, all transformed in ways that make them chemically and physically different from what they were before. A hominin approaches the burned area. This is normal. Burned areas attract scavengers because the fire kills animals that can then be consumed, because the burned vegetation exposes underground roots and tubers that were previously harder to access, and because the open post-fire landscape makes movement and detection of resources easier than in dense, unburned vegetation. The hominin has been using burned areas opportunistically for a very long time. They pick up something that has been partially heated by the fire. A tuber, perhaps, or a piece of animal tissue at the edge of the burn zone where the heat was sufficient to transform the tissue but not to char it completely. They eat it. And something is different. The texture is different, softer, more yielding. The flavor is different. Compounds released or transformed by heat create volatile molecules that register in the olfactory system in ways the raw version did not. Most importantly, the digestive experience is different. The cooked food is easier to chew, requires less time and energy to process, and delivers its calories more completely because the heat has already done some of the chemical work that digestion would otherwise have to do. Nobody in that moment understood what had happened or why it tasted different or why it was easier to chew. There was no eureka moment, no recognition that a transformative technology had just been discovered. There was just food that was different from the usual food. And the particular way it was different was appealing in ways that the ancient reward circuits of the hominin brain were perfectly calibrated to respond to. This is where cooking began, not with fire making, not with intentional application of heat to food, but with opportunistic consumption of accidentally heated food in the landscape. And from that beginning, one of the most transformative technologies in the history of life on Earth developed through a process of incremental adoption that took, depending on how you count and what you consider the threshold, somewhere between 1 and 2 million years to complete. The question of when ancient humans actually started cooking, when they crossed from occasionally consuming accidentally heated food to deliberately applying fire to food as a regular practice, is one of the most contested and most consequential questions in all of paleoanthropology. Because the answer is not just a date on a timeline, it is the answer to when the trajectory of the human species changed in fundamental ways that determined what we eventually became. Begin with what cooking actually does to food, because the transformative effects are the reason cooking was worth adopting, and the reason its adoption changed everything downstream. The word cooking covers a range of food preparation practices whose common element is the application of heat, but whose effects vary depending on the food type and the temperature and duration of heating. For starchy plant foods, tubers, roots, seeds, heat gelatinizes starches that would otherwise be resistant to digestion. Raw starch granules are crystalline in structure, largely impermeable to the digestive enzymes that break starch into glucose. Heated starch absorbs water, the crystalline structure collapses, and the resulting gelatinized starch is easily and completely digested. The caloric yield from cooked starchy foods exceeds that from equivalent raw starchy foods by 20 to 50% depending on the food and the cooking method. For protein-rich foods, meat, fish, eggs, legumes, heat denatures proteins, unfolding the molecular structure in ways that expose more of the peptide bonds for enzymatic digestion. Raw protein can be digested, but the efficiency is lower than for cooked protein. Studies comparing caloric extraction from raw versus cooked meat find that cooking increases protein digestibility by measurable amounts, and for protein consumed in large quantities as a dietary staple, this difference compounds into meaningful caloric gains. Cooking also kills pathogens, bacteria, parasites, viruses that are present in raw animal foods and that cause illness when consumed. In environments where large animal carcasses were a primary protein source and where scavenging behavior meant exposure to carcasses at various stages of decomposition, pathogen risk was a real and consequential factor in dietary health. Cooking systematically reduced this risk, improving the reliability and safety of animal food consumption in ways that would have had immediate survival value. Finally, Cooking reduces the energy cost of digestion itself. Digestion is metabolically expensive. The body must devote energy and time to breaking down food before it can be used. Cooked food, pre-processed by heat, requires less digestive effort and time than raw food of equivalent caloric content. Studies on the energetics of digestion find that animals fed cooked diets show different patterns of metabolic investment in digestion than animals fed equivalent raw diets. This reduction in digestive cost is a form of efficiency gain whose cumulative effect across a lifetime of eating is substantial. These effects together explain why cooking adoption, once it began, was essentially irreversible. A population that adopted regular cooking could extract more energy from the same food, access a wider range of food types safely, reduce illness from contaminated animal foods, and spend less time and energy in digestion. The competitive advantage over populations not yet cooking was real, and it operated continuously, not just in exceptional circumstances. The timeline of cooking's adoption is where the story becomes complicated, and where the most active scientific debate is concentrated. The earliest claim for controlled fire use by hominins, and by controlled fire, the evidence requires more than burned bone or charred plant material, which natural fires produce readily, but rather the hearth-like concentration of burned material in contexts unlikely to result from natural fire, comes from Wonderwerk Cave in South Africa, where researchers have identified burned bone and plant ash in sediments dating to approximately 1 million years ago. The evidence is not a hearth in the architectural sense, but a concentration of burned material that the site context makes difficult to explain by natural fire alone. More robust evidence of controlled fire use comes from Gesher Benot Yaakov in Israel, a site with excellent preservation conditions that has yielded burned wood, seeds, and flint associated with hominin occupation, and dated to approximately 790,000 years ago. The association of burned materials with hominin tools and other occupation evidence at this site, and the variety of burned materials suggesting intentional fire management rather than opportunistic exploitation of natural fire, has led many researchers to accept it as evidence of consistent, intentional fire use, considerably predating the latest dates sometimes cited for fire adoption. The Kesem cave sites in Israel, dating to approximately 400,000 years ago, provide some of the clearest evidence of structured fire use. Repeated burning in the same location consistent with maintained hearths, associated with burned bone in patterns indicating systematic cooking of animal food, and associated with hominin occupation evidence indicating sustained habitation with fire as a central feature of camp organization. In South Africa, the Pinnacle Point and Blombos cave sites provide evidence of fire use by anatomically modern humans approximately 164,000 years ago and later, associated with more sophisticated behavioral complexity, including the use of ochre, shell beads, and engraved geometric patterns. By this period, fire use was almost certainly a routine and sophisticated practice rather than an emerging technology. The European Paleolithic record, beginning approximately 45,000 years ago with the arrival of anatomically modern humans and continuing through the Upper Paleolithic, provides dense evidence of hearth use at virtually every well-preserved occupation site. Repeated fire use in the same locations, ash accumulation, structured hearth features with stone rings and pits, and burned bone in patterns consistent with systematic food preparation. The gap between the earliest and latest proposed dates for consistent cooking, somewhere between 1 million years ago and 200 to 300,000 years ago, reflects genuine uncertainty in the archaeological evidence rather than a simple problem of insufficient excavation. Fire evidence is difficult to interpret unambiguously because natural fires produce many of the same materials: burned bone, charred plant remains, fire-cracked rock that controlled fire use produces. Distinguishing controlled fire from natural fire in ancient deposits requires contextual analysis of the concentration, variety, and association of burned materials with other occupation evidence. And reasonable researchers examining the same evidence sometimes reach different conclusions. This is where Richard Wrangham's cooking hypothesis enters the story as one of the most influential and most debated frameworks in paleoanthropology. Wrangham, a Harvard Harvard biological anthropologist, proposed in his book Catching Fire that cooking was not just an adoption that improved human diet, but a co-evolutionary driver of the transformation from Australopithecus-like ancestors to the genus Homo, that the anatomical and physiological changes associated with the emergence of Homo erectus approximately 1.8 million years ago are most parsimoniously explained as adaptations to a cooked diet. The anatomical evidence Wrangham cites is substantial and has generated intense academic debate. Homo erectus shows a dramatically reduced gut relative to body size compared to earlier hominins. The human digestive tract is short relative to body size compared to other great apes. We lack the large fermentative colon that allows chimpanzees and gorillas to extract energy from raw plant material through microbial fermentation. This gut reduction implies a dietary shift toward more digestible food before or concurrent with the anatomical change, because a reduced gut with no dietary shift would result in inadequate caloric extraction and competitive disadvantage. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content, covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Homo erectus also shows reduced jaw size, reduced tooth size, and reduced facial prognathism compared to Australopithecus, a reduction in the masticatory apparatus that implies reduced demands on chewing in the diet. Raw food diets require extensive chewing. Chimpanzees spend approximately 47% of their waking hours chewing, while modern humans on typical cooked diets spend approximately 4 to 5%. The anatomical reduction in chewing apparatus from Australopithecus to Homo erectus implies a dietary shift that reduced the demand for extensive chewing before or concurrent with the anatomical response. The brain size increase that accompanies the emergence of Homo erectus from approximately 600 cubic centimeters in Australopithecus to 900 or more in Homo erectus fits the expensive tissue hypothesis, which proposes that the metabolic cost of a larger brain was funded by the simultaneous reduction in the metabolic cost of a smaller gut. The brain is metabolically the most expensive tissue in the body, consuming approximately 20% of caloric intake despite representing 2% of body mass. Funding this expensive expansion required either dramatically increased caloric intake or dramatic reduction in the metabolic cost of another expensive tissue. Gut reduction. The shift from the large fermentative gut of Australopithecus to the smaller, more efficient gut of Homo erectus represents exactly the metabolic reallocation that brain expansion required. The cooking hypothesis proposes that all of these anatomical changes, gut reduction, tooth, and jaw reduction, brain expansion, are connected by cooking as their dietary driver. Cooking made food more digestible, allowing gut reduction without caloric loss. Cooking made food softer, reducing the need for extensive chewing and the anatomical structures that support it. Cooking increased caloric yield from the same food, providing the metabolic surplus necessary to fund brain expansion without proportional increase in food intake. If Wrangham's timeline is correct, if cooking adoption drove the emergence of Homo erectus approximately 1.8 million years ago, then cooking began far earlier than the robust archaeological evidence currently demonstrates, with the hearth evidence from approximately 1 million years ago representing not the beginning of cooking, but a late stage in a practice already established for hundreds of thousands of years before preservation quality evidence survives. The opposition to Wrangham's early cooking date is substantial and worth taking seriously. The gap between 1.8 million years ago and the earliest reasonable archaeological evidence for controlled fire at approximately 1 million years ago requires assuming that cooking was practiced without leaving detectable hearth evidence, either because fire management at that early stage was too diffuse to produce concentrated hearth features, or because preservational biases in the fossil record have systematically missed the relevant sites. Both explanations are plausible. Early fire management might have involved using existing natural fires rather than creating and maintaining dedicated hearths, heating food on or near a natural fire without establishing the repeated use hearth structure that preserves archaeologically. And the fossil and archaeological record from 1.8 to 1 million years ago in Africa, the region where early Homo erectus was most abundant, is fragmentary enough that substantial evidence could be missing simply from inadequate site preservation rather than absence of the practice. Alternative explanations for the anatomical changes associated with Homo erectus including dietary shifts to more meat without cooking, or increased use of underground tubers with mechanical but not thermal processing, or food sharing and social food transport that changed the energetics of dietary acquisition without requiring cooking, have been proposed and debated. None of them as completely accounts for the full suite of anatomical changes as cooking does, which is why Wrangham's hypothesis has remained influential even as it has attracted significant criticism regarding the early timing. The behavioral and cognitive consequences of cooking adoption are arguably as significant as the physiological ones, and they are less often discussed in the archaeological and biological literature that focuses on anatomical evidence. Cooking requires fire. Fire requires either making fire from scratch through friction or percussion, or maintaining fire once obtained. Both require sustained attention to the fire's needs: fuel, oxygen, protection from rain and wind, and planning for the future in a way that foraging for immediate consumption does not. A hominin that maintained fire across a day of foraging was simultaneously tracking immediate needs: find food, avoid predators, and future needs: ensure the fire is still viable when we return to camp, in a way that requires working memory allocation beyond the immediate moment. Cooking also decouples food acquisition from food consumption in time and space. Raw food is typically consumed close to where it is found, in the immediate aftermath of acquisition. Cooking creates the camp as a food preparation site. The concept of bringing food back rather than eating it in the field, and the social dynamics of food sharing that a communal cooking area enables. The camp organized around a fire, and cooking activity is a qualitatively different social environment than a dispersed group consuming food individually in the field. And the cognitive and social demands of this new environment, managing who contributes what, who is entitled to share in prepared food, how food is allocated across group members with different access to raw materials, may have been a driver of social complexity and cognitive development. The role of cooking in gender division of labor has been proposed as another significant social consequence of cooking adoption. The consistent pattern in traditionally living human societies of cooking being primarily women's work, with men typically responsible for hunting large game, and women for gathering plant foods and food preparation including cooking, may reflect an ancient division that emerged when cooking itself became a significant time investment. The daily labor of food preparation, fuel gathering, and fire maintenance associated with cooking is substantial, and its assignment within groups would have been organized by the same social mechanisms that allocated other labor. The sensory and cognitive dimensions of cooking, the development of food knowledge about what cooks well, how long different foods require, what temperatures and methods are optimal for different food types, represent accumulated practical knowledge of substantial complexity. Hunter-gatherer food preparation knowledge documented in contemporary and historical traditional societies is far more elaborate than casual observation suggests. The preparation of specific plant foods to remove toxins, the optimal cooking methods for different game animals, the ways of preserving food through smoking and drying that extend its viability, all represent knowledge accumulated and transmitted across generations as a technical tradition of real sophistication. This knowledge tradition is, in a sense, the oldest culinary tradition in human history, not in the modern gastronomic sense of food culture, but in the practical sense of accumulated, transmitted knowledge about how heat transforms food and how to use that transformation to extract maximum nutritional value from available resources. The archaeological evidence that most directly documents ancient cooking, beyond hearths and burned bone, comes from dental calculus analysis, the study of preserved plaque mineralized on ancient teeth that retains traces of what was eaten. Analysis of dental calculus from ancient hominins has identified starch granules in patterns consistent with cooked starch rather than raw starch, and the presence of these patterns in Neanderthal dental calculus from sites predating the arrival of anatomically modern humans in Europe provides evidence that cooking was practiced by archaic human populations independently of whether it was specifically a modern human innovation. The dental calculus evidence reinforces the picture of cooking as a very ancient practice that was almost certainly established across multiple hominin lineages before the emergence of anatomically modern humans. Not a uniquely modern human capability, but a deeply hominin one, arising from the basic intelligence and fire management capability that preceded our species by hundreds of thousands of years. When did ancient humans start cooking? The honest answer encompasses multiple timelines operating simultaneously. Opportunistic consumption of naturally heated food almost certainly began with the earliest hominins, whenever they first encountered burned areas areas after natural fires and found the heated food more palatable. Intentional cooking, the deliberate application of controlled fire to food, probably began somewhere between 1 and 2 million years ago, in a form too diffuse and primitive to leave clear archaeological hearths. Consistent, reliable, culturally transmitted cooking practice with structured hearths and systematic food preparation is clearly documented from approximately 400,000 years ago, and probably substantially earlier. The person who first tasted accidentally cooked food at the edge of a wildfire thousands of generations before Homo erectus had no idea what they had started. They tasted something that was better than what they were used to, and they ate it. And they came back to burned areas looking for more of it. From that beginning, from the preference for food that tasted different, that was easier to chew, that filled them up better, the entire cascade followed. The smaller gut, the bigger brain. The camp organized around fire. The social complexity of shared meals. The culinary traditions of every culture that has ever existed. It all started with someone eating something warm and finding it good, and then doing it again.